Okay, guys, this is a very quick run through the Arrhenius equation calculation, or one that you might see on your exam. So here we have the Arrhenius equation, which you'll remember from chapter 14, and it's a way to calculate the rate constant based on activation energy, the temperature of the reaction, and the gas constant R. And I won't go into all the components, but you can, if you notice, the temperature is in the denominator here of this exponent, and if you raise the temperature, you can raise K and cause the reaction to go faster. Lower the temperature, you can cause the reaction to go slower. And you can compute the differences in the rate constants by subtracting the natural log of K2 minus the natural log of K1, and expressed using logarithmic rules, you can simply express them as the natural log of the ratio of K2 over K1. And if you do that and you solve for this component right here, this is what you get. The natural log of K2 over K1 is equal to E of A over R times 1 over the Kelvin temperature for K1 minus 1 over the Kelvin temperature for K2. You might also see this expressed as the natural log of K2 over K1 is equal to minus E of A over R times 1 over T2 minus 1 over T1. All I did was multiply through with the negative sign, which is just causes the inverse of the temperatures to switch places here, because you have negative times a negative, which will make this a positive. Negative times a negative makes that a negative, and so these two just switch places. It's exactly the same equation. It's just rearranged, so I don't have to deal with the negative sign. And I prefer this version, but you can use either one. All right, so let's look at this problem. It gives us an activation energy, this guy here, of 262 kilojoules per mole, and down here the gas constant R, which you can look up, is 8.3145, and that's in joules per mole Kelvin. What you need to do is either convert kilojoules to joules or joules to kilojoules. You convert joules to kilojoules by dividing by 1,000, and you convert kilojoules to joules by multiplying by 1,000, and I think that's what I'm going to do in this particular case. The kilojoules will cancel, and I'll have it in joules, and that'll simply be equal to 262,000 joules per mole. Okay, so now that we've done that, let's go ahead and just plug our values in. We've got 262,000 joules per mole, and down here in the denominator we've got 8.3145 joules per mole times Kelvin temperature. Okay, and then we'll open up our parentheses, and here we've got 1 over T1 in the version that I've chosen to use, and so that's going to be 1 over the initial temperature. This is T1, then this is K1 that's associated with the initial temperature. So that's going to be 1 over 600 kelvins minus 1 over T2, and T2 is given at 815 Kelvin. So that'll be 1 over 815 Kelvin. Let's take care of the units. So joules will cancel, moles will cancel, and this is inverse kelvins, and this is 1 over kelvins, which is equal to kelvins over 1, so the kelvins will also cancel. All right, so if I do that, what I wind up with is that the natural log of K2 over K1 is equal to 13.85 approximately. Now, to get rid of the natural log, I just take the E of both sides of this equation, and what I come out with is that the ratio of K2 over K1 is equal to 1.04 times 10 to the 6. What this is saying is that the rate constant at the higher temperature will produce a reaction that is 1,000,000 times faster. So that's 1,000,000 times faster, and all I did was I raised the temperature of the reaction, get the same activation energy in both cases. It's times faster than it is at the lower temperature. And that was only a difference of 215 Kelvin. That is from 600 Kelvin to 815 Kelvin, and a tremendous increase in the temperature. Now, that's not actually what we're after in this particular problem. In this problem, we want to know what K2 is, and so since we know that K2 over K1 gives us 1,000,000, all we have to do to find K2 is multiply K1 times that ratio. And so this is just going to be K1 times the ratio of K2 over K1. And that is going to be 6.1, it's given right here, 6.1 times 10 to the minus 18 times 1,000,000, which is 1.04, a little bit more than 1,000,000 actually, times 10 to the 6. And when I work that out, I wind up with 6.3 times 10 to the minus 12, and the units on K1 are per second. It's first order. And so this is times 10 to the minus 12. These will also be units of per second because it is a first order reaction. Okay, so that's how you would use this expression, this version of the Arrhenius equation. You could also use this. Just keep in mind that if you use the version that has the minus sign out in front of E of A, you've just reversed T2 and T1 in the equation. Either way works the same.